So again, talking about parasitics, another place where parasitics come into play is when you have interconnects. And so there are these different levels of interconnect, local, semi-global, or intermediate and global. But for these global and your semi-global interconnects, the most dominant delay is this RC delay, which is coming from the resistance of the line and its capacitive coupling with all these other electrodes. So when we talked about another application where parasitics are increasingly becoming more and more important is your NAND flash memory. So your NAND flash is this regular bit lines and word lines. And you can see that your parasitics, in this case, these parasitics between your bit line and your word line and all these other diagonal parasitic elements, they can be up to 50% of your, so this, these different components are each around 10% range, but if you add them up, these are up to 50% of your total capacitance is just these bad parasitic capacitance. So let's take a closer look at it. So what is shown in black over here are the good capacitances. That is capacitance between your floating gate and your channel, and your floating gate and your control gate. But you get these all red capacitances, which are bad capacitances. And these fringe capacitances can be up to 50% of your total capacitances, of your total self-capacitance of your floating gate. So as you can see, and they'll become even worse if you bring these bit lines and word lines closer. So this is something which is becoming even more bigger of a problem as you scale these devices. So wouldn't it be nice if I replace that yellow thing which is bothering Kathy with with air? So if I can replace that yellow thing with air, and I can replace this dielectric in between with air, right? So that brings me to the next thing I want to talk about. That is air gap. So air gap is essentially a way to reduce this capacitive coupling between either two adjacent metal lines. So shown here is this air gap introduced between two copper lines in an interconnect, and it reduces my capacitances by half at the same resistance. So I'm not doing anything to the copper line, so its resistance stays the same, but my capacitive coupling is reduced by half. So my RC delay is reduced by half. If I replace this dielectric by air, air also has the largest band offset you can get. So my leakage between these two adjacent lines, again, that reduces by 2 orders of magnitude if I replace the dielectric with an air gap. If you introduce an air gap, essentially it builds some amount of stress immunity into it. So if there's an air gap, it can absorb the stress. So it improves your electromigration performance of your electrode. And so you get all these extra benefits by introducing air gap as well. So air gap is routinely used now in logic technology. It's also used by now I think 3 out of the 5 main NAND flash players. They use air gap. So shown here again are these 3 transistors along a bit line, and you can see there's a very controlled air gap introduced between these transistors, and that reduces your floating gate to floating gate coupling substantially. And that also results in a very tight distribution of your threshold voltages in your NAND flash. So the next the next big question we need to answer is, how do I make these air gaps so controllably between these adjacent features, which are just a few nanometers apart. So next I want to talk about is, how do I make these air gaps, and what are the different techniques of making air gaps. And so this is one technique. It was publicized by IBM quite a bit in 2007. And the way it works, it uses a sacrificial polymer. So let's say I have those copper lines patterned I fill it up with this polymer, and then I fill it up with this dielectric. And the unique thing about this dielectric is that it's porous. So it has these pores inside it. So there could be multiple ways you can make it porous. The way IBM used to do it was it used to do self-assembly and then etch those pores into this dielectric. So you can make pores into this dielectric, and then you can do either of two things. You can heat it up such that if this polymer has a a lower evaporation temperature, it will just evaporate out of that pores. Or you can bring a chemical in from the pores, and then you can remove this polymer. So either way, either you can evaporate your polymer out, or you can etch it out. And this is the way then you get an air gap between these structures. Both of those ways have their own issues. If you heat it up, you typically need to heat it up above 400 degrees centigrade, and that's not good for your transistors, which are below these interconnects. And if you wet etch it, again, it can cause these copper line to corrode. So again, very well publicized technology, but not really used. Another way to make air gap is something that you can turn a problem on its head and use it to make actually something useful. So this is something where we saw that our CVD process has a non-conformal nature because you get a much larger flux when you're doing a CVD at the top, and you get a much lower flux when you're deep below this trench. So by just being by the inherent nature of your CVD, you get that this closure in your profile. And if you just keep on going along that path, you essentially get a closure between these two fronts, and these two fronts on the top meet, and they leave an air gap in between. So this is something which is used, by almost everybody who uses air gap. And the two important things is that when these two fronts meet, they leave a seam in between. So it's very important to close these seam off. And typically people change their plasma conditions such that it becomes a more conformal deposition once you have formed the air gap. So you seal this seam off. Once you have sealed it off, again, you don't want to open it up again. So once you have sealed it off, you want to make sure that it remains sealed. So when you are doing a planarization step, say like CMP, you want to make sure that you don't expose that air gap again. So you don't want to go back to this state where this air gap would become open again. So, but this is something which is used by everybody. Another advantage of doing making air gap this way is that it gives you air gaps where you want it. So if you have these multiple features with different widths, you'll get an air gap only in the smallest feature. These other features which are big will still give you a fill which fills up the whole structure. So air gap will be formed only in narrow trenches, and in fact that is where we need the air gap the most. If these are two metal lines, the place where the capacitance would be most is when they're closest to each other. So good thing is that it gives you air gap where you need them. It doesn't give you air gap where you don't need them. Another thing another technique, I just want to mention it in passing, but it's not again used by anybody. But most of these air gap schemes are essentially, they have to be repeated at every level. So your metal, in your microprocessor, you have these 9 levels of metal, and if you want to form air gap at each level, you'll have to repeat them at every level. A cool technique which was proposed by Toshiba is you essentially etch out a pore, and you make this pore which connects these multiple levels, and you essentially do a wet process to remove all your dielectric, right? So you need these metals, you don't really need dielectric in between them, right? So you create that, you create like a suction and you remove all your dielectric out. But again, the problem is that the whole thing collapses, so nobody actually uses it. Now the next theme I want to talk about, and I want to cover a few things talking about that theme is which is again becoming very important, is the interface. And so I'm pulling up this picture of Herb Kromer, and he's a professor in Santa Barbara and also a Nobel Prize winner. And if you know, there have been only 2 Nobel Prizes in semiconductor. One was Shockley Bardeen, and the other one was Kromer and Kilby, and they shared this Nobel Prize. And the research of Kromer was around heterostructure and heterostructure interfaces. And he said in his Nobel lecture that, and you can go, I've given up the link over here, you can go and there's a video over there, you can watch it as well. So what he said was, essentially he was struggling with making these hetero interfaces between these 2 different semiconductors. And what he said, after many, many years of research, he realized that the interface is actually the device. And you actually see that happening across different spectrums of devices currently, where interface is becoming the important thing. And the reason is that as you scale, your surface area increases and your volume decreases. So your interface, and the way I'm defining interface volume over here is just multiplying my surface area by 1 nanometer. So I'm calling that top 1 nanometer of volume as my interface volume. So in a 90 nanometer planar device, your interface used to be 1% of your device. In a FinFET device, when you want these tall and thin fins, 15 or up to 15% of your volume is essentially your surface volume, or your proportion of your surface area or your interface of your device is just becoming more and more a larger percentage of your total volume. And this is causing a lot of challenges as well as opportunities. Some people use it as opportunity. There are devices which leverage this phenomena. Topological insulator is one. Metal oxide-based transistors are one. But we are not covering that in this course. But for the devices that we are covering in this course, it's becoming a major challenge. The same thing is happening in interconnects. And if you talk about a 90 nanometer interconnect, only 1% of that surface volume is just 1% of your total volume. In a 20 nanometer interconnect, the interconnect becomes skinnier and it becomes longer. So it's again 5 to 10% of your volume is your interconnect. And so there are 3 different interface you can talk about. You can talk about semiconductor dielectric interface that occurs when you make your gate stacks. You can talk about interface between 2 metals that occurs when you're doing your back end of the line process. So you have copper, and you want to you put a layer which prevents it from diffusing it, which is a barrier or a liner layer. So there's an interface over there. There's also an interface between your semiconductor and your metal that occurs when you're forming that silicide or you're forming that source and drain contact. So, what is the mobility of silicon? So, silicon on a bulk has a mobility of 1600 for electrons. It has 430 for holes. Some of these new alternate channel materials have much higher mobility, but what is the mobility you actually get in your transistor? So as I mentioned, silicon has a bulk electron mobility of 1600. When you make a transistor, you get something which is 1/8 of that. In current technology, if you look at those Intel transistors and extract the mobility from them, they won't have a mobility of more than 100. So what's causing this 10 times reduction or 5 times reduction in my mobility? And the reason is most of that mobility decrease at that high electric field or that scale device is because of my interface. So it's because of my scattering at the interface. And this is again becoming more and more of a problem as you go down the scaling path. So over here, I'm repeating this slide from our discussion on FinFETs. So my FinFET, the only way they scale is if I scale my width. So if I scale the width of my silicon, if I need to scale the gate length. So if I scale the width, essentially if I make my fins taller and thinner, the part which is my interface or my interface volume, that just keeps on increasing, and as I make it more and more thinner, I get even more scattering from the interface, and I get an even sharper drop in my mobility. So this is something which is, interface is becoming a key. The same story repeats when you go to alternate channel material. Another interesting thing. So interface between two metals, right? So let's say this is a question I want to pose, that if I have a metal, say copper, it has a resistance of say R2, and I have this barrier on top, say tantalum nitride, and it has a resistance of R1. What happens if I put that tantalum nitride on top of my copper? What is the overall resistivity of this combined stack? So we learned Kirchhoff's law in our undergrad, that resistance of two parallel things should be just this R1 R2 divided by R1 R divided by R1 plus R2, and that's always less than, it's a geometric mean of two things, so it should be less than each of these individual things, right? Yeah, so the actual answer is that it is higher. So here's some experimental data. So this is a copper film which had a resistivity of around where this is 0.63, and when I deposit tantalum nitride, tantalum on top, the resistivity of the overall stack is actually decreasing, right? And if you believe that this one data is not true, then there's this another data, and it shows the same trend, that if you have copper and you deposit that tantalum on tantalum nitride on top, and if you deposit a very thin film, the resistivity of that overall stack is less than the resistivity of this individual layers. And the reason is essentially scattering at the interface. So if you have two of these metals in parallel, if you have an elastic scattering, then it's okay. If something comes back and if something goes from this low resistivity copper into the tantalum and comes back with the same momentum, then it's fine. But if you have a non-elastic scattering, which is the case when you have boundaries between two metals, then your overall resistivity decreases. The best analogy I know of to explain this is, think of you're driving on 101, right? How many of you commute to Stanford? Okay, so if you commute between 8 to 9 on 101, there's this diamond lane, or we live in California, right? So there's this carpool lane which goes very fast, right? And these are these other lanes which are really slow. So the question is, are these other lanes which are basically not moving, right? It's a parking lot on the other lane, and then this diamond lane which is moving. So are those other lanes slowing my carpool lane down, right? So the answer depends upon whether I can just stay in my carpool lane. So if I'm in my carpool lane and I'm with a buddy of mine and we are going on 60 and 70 and we just stay on that, it won't bother us, right? So we have these other cars which are going really slow, are not going anywhere, but as long as I stay on my lane, I won't be affected. So that's the case if you have these disconnected resistors, right? But if I put a boundary condition that I can stay in the carpool lane only for 5 minutes, and then I have to scatter out of it, right? So every 5 minutes, I have to go out of the carpool lane into these other lanes which are not really moving, and then come back to my carpool lane. It will slow me down, right? So that's exactly what happens. Your electrons are going fast in here, but eventually, once a while they get lost and they scatter into these high resistivity layer, and when they come back, they lose their momentum. And that brings the overall resistivity of your overall stack down. Another interface is this metal semiconductor interface. So again, I want to just mention that this is again becoming a main problem again. And so Deepu, who's the speaker on Wednesday, will talk about it in great length, so I don't want to cover it. Any questions on interface? the last theme that I wanted to cover was related to the physics and chemistry. So we'll have this in problem set. So what it requires you is we'll cover this, I think, using the problem set, but it requires a lot of understanding of your strain and ALD, and I'll post additional videos about it, but I'm out of time to cover it now.